Interference is the phenomenon that occurs when two or more waves overlap, leading to a new wave pattern. It is a direct consequence of the superposition principle, which states that the resultant wave at any point is the sum of two individual waves. The energy of a photon is given by E equals HF E equals HF, where H is Max Planck's constant. Polarization refers to the orientation of the electric field vector. EM waves can be polarized in various ways, linear, circular, or elliptical, describing the trajectory of the electric field in the plane perpendicular to the direction. Black body is an idealized object that absorbs all incident electromagnetic radiation regardless of the frequency or angle of incidence and re-emits this energy perfectly according to its temperature. The radiation emitted by such a black body is known as black body radiation. There are many rules that govern black body radiation, namely Planck's law. The spectral radiance of a black body at temperature TTT is given by Planck's law. BVT equals 2hv cubed over c squared times 1 over e to the power of hv over kt minus 1. K is the Boltzmann constant, c is the speed of light, h is Planck's constant, T is the absolute temperature. Another law is known as Boltzmann constant, which is Another important law is Boltzmann's waves and space. Transfer energy without moving matter. A wave is defined as a disturbance in a medium that carries energy without a net movement of particles. The Doppler effect is the observed change in the frequency of a wave in relation to an observer who is moving relative to the source of the wave. Redshift is the observed increase in the wavelength of light received by Earth from distant galaxies, showing that the light received is redshifted, and this can provide evidence for the universe's expansion. This shows us that distant galaxies are traveling away from us, just like the Doppler effect observed with cars. When cars pass us, there is a sudden shift to a lower tone/pitch. This is because, as the car is moving away, the wavelength of the waves that reach us are higher as it is traveling away from us, and these specific waves with these specific longer wavelengths are the ones that are able to reach us. Which means that with a constant speed, the frequency of the waves will be lower. Therefore, in terms of sound waves, this will lower the pitch. These distant galaxies moving away from us also provide evidence for the Big Bang, as it shows us that the universe dilates from a single point where all the matter is theorized to have an unstable form of energy. This point of all of the matter in the universe exploded in the Big Bang, releasing matter into space, expanding the universe despite the constricting forces of gravity, which results in further objects traveling further away from each other due to a central dilation of the universe originating from a point in space. Picture this as an object here with another object here, and you see that as the space between them expands, this will greatly expand, almost exponentially, the space between the objects themselves. Now we can observe evidence from these galaxies being redshifted that the universe is expanding at an ever faster rate. Let's take a look at the life cycle of stars. First, high temperatures allow hydrogen to fuse into helium efficiently, kick-starting the stable period of the star, which is known as the main sequence stage, where the forces of gravity pushing inwards are balanced with the radiation from pressure from the energy. Originally, however, nebulae must cluster together as collections of dust and gas to form a protostar, with the internal pressure of the gases releasing heat and energy to start nuclear fusion. When the temperature exceeds 10 million degrees Celsius specifically, nuclear fusion of hydrogen into helium is very efficient, allowing the star to expand, and it becomes a main sequence star, where the forces of gravity pushing inwards are balanced with the radiation pressure forces pushing outwards. This is the stable period of the star. However, when the star begins to run out of hydrogen fuel to fuse into helium, it collapses until the pressure is so great that the star begins to fuse heavier and heavier elements. This continues all the way up to iron, which is known as a dead end, as an equal amount of energy is released from its fusion as energy needed to be put in. The star then begins to fuse these heavier and heavier nuclei together, growing into a red giant if it has a similar mass to our Sun, or into a red supergiant if it has a much greater mass than our Sun. This continues until iron is reached, and if the star is a similar mass to our Sun, the red giant will collapse under its pressure to form a white dwarf. and the dense core of the star as the forces of gravity press inwards, and this will gradually cool to form a black dwarf. If the star has a much greater mass than our Sun, however, one of two things may happen, depending on its size. If it has a greater mass, it will most likely collapse under amazing forces of gravity and will become a neutron star, which is the dense, hot core that will remain after this, which can lead to phenomena such as spinning neutron stars emitting light from distant galaxies and many more interesting observations. However, if the star has a much greater mass than our Sun, it will collapse in on itself under its own forces of gravity and will form a singularity, which will then form a black hole. A black hole's gravity is so powerful that not even light can escape from it. As you can see in this diagram, the light must bend around the black hole to escape. Otherwise, once it goes into the center, into the singularity, it can never come back out again. Electromagnetic waves are very interesting, as the electric field waves are perpendicular to the magnetic field waves, which are perpendicular to the direction of motion, which is the force, which exhibits even, Fleming's left-hand rule. Ultrasound is any wave that is above the human hearing range of 20 kHz, and is used in medical imaging by using the times ultrasound waves are reflected back to produce images of babies and of the body. Electromagnetic waves are fundamental phenomena in physics, combining the properties of electric and magnetic fields. As we know that an electric field is a space with a particular property that if a charged object is placed within that space, a force will be exerted on it, and similarly a magnetic field has a similar property, exerting a magnetic force which cannot be seen, only its effects can be observed. These waves are essential for understanding a broad range of physical interactions and are used extensively in various technologies. Here's a detailed explanation of their properties and functions. Transverse nature. Electromagnetic waves are transverse waves, meaning that the oscillations of the electric and magnetic fields are perpendicular to the direction of wave propagation. The electric field oscillates in one plane, and the magnetic field oscillates in a plane perpendicular to this plane. In a vacuum, all electromagnetic waves travel at the speed of light, denoted as c, which is approximately 300,000 km per second. The speed of electromagnetic waves is in a medium is less than the speed of light, and it depends on the medium's properties, described by the refractive index. Is a very important phenomena, and it is denoted by Snell's law, which states that n1 times sine theta 1 equals n2 times sine theta 2. The energy of an EM wave is quantized and is carried by particles called photons. The energy of a photon is given by E equals HF E equals HF, where H is Max Planck's constant. Polarization refers to the orientation of the electric field vector. EM waves can be polarized in various ways, linear, circular, or elliptical, describing the trajectory of the electric field in the plane perpendicular to the direction of propagation. The electromagnetic spectrum encompasses all wavelengths and frequencies of the EM waves, from very long radio waves to very short high-energy gamma waves. The main categories are radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Functions and applications of electromagnetic waves. Communication. EM waves are the backbone of all wireless communication systems. Radio waves are used in broadcasting, cellular network. EM waves are the backbone of all wireless communication systems. Radio waves are used in broadcasting, cellular networks, and satellite communications. Microwaves are utilized in Wi-Fi and Bluetooth technologies. X-rays and gamma rays can also be used in medical imaging and treatment, for diagnosing in the body, for creating diagnoses. Infrared and radar technologies are used in weather forecasting, surveillance, and environmental monitoring. Infrared cameras detect heat signatures, while radar systems measure distances and speeds. The global positioning system is also based on these fundamental electromagnetic waves, namely in the microwave range. EM waves from various parts of the spectrum provide information about the universe, and they are used in astronomy in particular, such as radio telescopes and X-ray and gamma ray telescopes, to study high-energy phenomena like black holes and supernovae. They can also be used in spectroscopy and as lasers. Electromagnetic waves are versatile and pervasive in both natural phenomena and technological applications. Their properties such as transverse oscillation, speed, wavelength, frequency, and polarization dictate their behavior and utility across different fields. From enabling wireless communication and medical imaging to facilitating astronomical observations and industrial processes, electromagnetic waves play a crucial role in modern science and technology. Black body radiation is a critical concept in astrophysics and other fields, providing insights into the thermal properties of astronomical objects. Here's a detailed explanation of black body radiation as an astronomical phenomenon and its consequences. A black body is an idealized object that absorbs all incident electromagnetic radiation, regardless of frequency or angle of incidence. A fairly good example of this in the universe is the black dwarf, which we mentioned earlier. And this black body re-emits this energy perfectly according to its temperature. The radiation emitted by such a black body is known as black body radiation. Wien's displacement law is characterized by L max T equals B. Stefan Boltzmann law is also another characteristic of black body radiation. In astronomy, stars can be approximated as black bodies, with their spectra providing information about their temperatures and size. The Sun, for example, has a surface temperature of about 5,800 Kelvin, emitting a spectrum that peaks in the visible light range. By applying Wien's law, astronomers can estimate the temperature of a star from its color. The Stefan Boltzmann law allows for the calculation of a star's luminosity based on its temperature and radius. Cosmic microwave background. The CMB is the residual thermal radiation from the Big Bang, acting as nearly a perfect black body, with a temperature of about 2.725 Kelvin, which is almost absolute zero. The CMB provides critical evidence for the Big Bang theory and helps cosmologists understand the early universe's conditions. Planetary and stellar atmospheres. Planets and other bodies with atmospheres emit black body radiation in the infrared range, allowing for the temperature measurements and climate studies. Infrared observations of planets can reveal details about their atmospheric composition and surface conditions. While black holes themselves do not emit radiation, the surrounding accretion disks can be approximated as black bodies, with X-ray emissions providing information about the matter in fall and relativistic effects near the event horizon. Once you cross the event horizon, we know that you can never leave it again. Black body radiation serves as a foundational concept in understanding the thermal emission of astronomical objects. Its principles, including Planck's law, Wien's displacement law, and the Stefan Boltzmann law, enable astronomers to determine temperatures, classify stars, and study the universe's evolution. This understanding provides insights into the physical properties and processes governing stars, planets, and the cosmos, making black body radiation a cornerstone of modern astrophysics. When light travels through a different medium, it refracts. The speed of light decreases from air to glass as there are more particles in a tight structure, so light is being absorbed and re-emitted, which slows down light, causing it to refract, as you can see in this diagram here. Here we see light bend towards the normal, drawn perpendicular to the medium, as well as the wavelength decreasing so that the frequency stays constant. Funnily enough, it does not work the same way as electromagnetic waves. Here you are trying to maintain the frequency of the source of light, which is the only thing that stays constant, rather than the speed of the wave, which is the case with electromagnetic waves. As a result of slower travel, the wavelength decreases, creating shorter distances between the frequency of light rays, so light must compensate by bending towards the normal to preserve the light rays' frequency, as the frequency is characteristic of the source of the light, which is the only thing that doesn't change. From a detailed view into redshift, we can draw strong universal links. Certain elements on the Earth absorb different wavelengths of light, so certain wavelengths are missing on our absorption spectra. When light from distant galaxies reaches Earth, due to the galaxy appearing to be moving away from us, reaching us will appear to be redshifted towards the longer wavelengths. However, this is not due to the movement of galaxies. Instead, it is due to the space between us and the galaxies expanding itself, as I demonstrated in an earlier explanation, where the redshift can help us conclude that the universe is expanding at a faster rate. This is why more distant galaxies appear to be more redshifted, because as there is greater space between them expanding, a greater speed of travel away from us can be interpreted due to the dilation of the universe, and in effect wavelengths of light reaching Earth appear to be more redshifted. In contrast, we can infer from the Andromeda galaxy moving closer to us through space to result in blue shift, with waves likely getting compressed due to the shorter wavelengths of light that reach us, and this decreased wavelength will in fact increase the frequency as the vacuum of space as well as the laws of physics serve to preserve the constant speed of light. C. Wave-particle duality is a cornerstone of quantum mechanics, revealing that particles such as electrons and photons exhibit both wave-like and particle-like properties. This duality was first brought to light by experiments such as the double-slit experiment. Interference is the phenomenon that occurs when two or more waves overlap, leading to a new wave pattern. It is a direct consequence of the superposition principle, which states that the resultant wave at any point is the sum of two individual waves. Consider the classic single-slit experiment. When monochromatic light passes through a narrow slit, it diffracts and forms a pattern on the screen placed behind a single slit, and it displays the properties of a particle, that particle namely being a photon. This pattern consists of a central bright fringe flanked by alternating dark and bright fringes. The central maximum is the result of constructive interference where the diffracted waves are in phase, while the dark fringes result from destructive interference where the waves are out of phase. Mathematically, the position of these fringes can be described by the equation a sine theta equals m lambda over sine theta equals m over lambda a sine theta equals m lambda, where a is the width of the slit, theta is the angle relative to the original direction of the wave, m is the order of the fringe, and lambda is the wavelength of the light. Wave-particle duality. In the double-slit experiment, when light or even electrons passes through two closely placed slits, an interference pattern emerges on a screen behind the slits, similar to that of water waves interfering. This pattern consists of a series of bright and dark fringes, as you can see on this panel, indicative of wave-like behavior. Now we can interpret light to be a wave. However, when the intensity of the light is reduced so that the photons pass through the slits one at a time, individual impacts can be detected on the screen, when they are acting like particles, in fact. Surprisingly, over time, these individual impacts also form the same interference pattern. This implies that each photon, though behaving as a particle when detected, travels as a probability wave through both slits simultaneously, interfering with itself. This duality is encapsulated in the concept of the wave function psi, which describes the probability amplitude of a particle's position and momentum. The squared magnitude of the wave function gives the probability density of finding the particle at a particular location. This is where we start to see the idea of the superposition principle. Interference is the phenomenon that occurs when two... There are two types of interference, constructive and destructive. Constructive interference occurs when the crest of one wave coincides with the crest of another, resulting in a wave of greater amplitude. Destructive interference occurs when the crest of one wave coincides with the trough of another. Evidently, we can see this as a simple example with the sine wave and the cosine wave, leading to a reduction in amplitude or complete cancellation. Interference is vividly illustrated in the double-slit experiment, where the waves emanating from the two slits combine to produce an interference pattern of alternating bright and dark fringes. The position of these fringes can be described by the equation d sine theta equals m lambda over sine theta equals m lambda, where d is the distance between the slits, theta is the angle relative to the original wave direction, m is the order of the fringe, and lambda is the wavelength of the light. These concepts form the bedrock of modern physics, giving us a deeper understanding of the quantum world, and on that note, we will leave that video right there. Thank you for watching this waves video, and make sure to check out our other physics videos, namely the nuclear fusion video.